the CCNA journey with me, Ryan, and in this section we're going to go over the cabling overviews. This is for section 1.3 under the network fundamentals of the blueprint. Here we'll go over copper and fibre cabling. One thing to note is this video here is actually pre-recorded back for the CCNA or the ICND1. I've copied it because all of the content is identical to what you need to know for the CCNA. For those who don't know, you can contact me here on YouTube, Facebook, LinkedIn or Twitter. Okay, so first let's have a discussion around copper and fibre, the differences between them, and understand some of the reasons why we might want to use one over the other. First, let's talk about copper. Copper itself uses the electrical signals to communicate with one another. So if we imagine that we have two PCs, these electrical signals will be interpreted by both the layer 1, which is the physical, and layer 2, which is the data link, in the OSI, Open System Interconnect model. And essentially between these two devices they were able to determine that if there was an increase in voltage, that may specify a 1 in binary, and if there's a decrease in voltage, it would be able to identify it as a 0 in binary. If there is a higher than normal voltage on the wire, then they could indicate that there was some sort of collision, and they do that using the carrier sense multi-access with collision detection. And that's a protocol that's used at Ethernet at layer 2, and we will understand that in more detail in the videos to come. We know that it's affected by interference. So if you had a electrical source and you had to run some copper cabling beside it, there's a good chance that that interference is going to scramble the information inside. And because the voltage levels are used to indicate the binary information on the wire, that could corrupt the actual signals themselves, and when the data link layer actually goes through the CRC check, the redundancy check of the actual message itself, it will show up as corrupt and therefore will have to be retransmitted or dropped. It's cheap, so copper itself, you can pick up your copper cabling, primarily known as Ethernet, which is the twisted pair type of cabling. Very cheap at a local store, and it's easy to create. With copper cabling, depending on the length of cable you require or the type of cable, whether that's the different types of cables like rolled cables or maybe the crossover cables and straight through cables, you can actually cut the ends of the cable off, turn the pairs into the correct way to change the type of cable. You can also cut the cable in half if you want a short cable, or buy a long reel of cable and create your own ones. Essentially, it's a much easier way of doing it. And comparing that with fibre, the transmission is via light. Now that's either LED or laser depending on the type of fibre that you've purchased. The light is a bright light that actually shines out of the end of the cable, so don't look down it will damage your eyes. There's no interference, so if there was any electrical sources that we had to run our cable near, then let's use fibre, yeah, because we don't want those external interference to impact the integrity of our data. And the distance. Copper cabling, depending on the type of cable, tend to go up to 100 meters or so. With fibre, it can go much further. We have two different types of fibre. We have something called multi-mode and single mode. In the multi-mode fibre, it's actually basically like this. You have your fibre itself, and a light will come into the fibre, normally an LED with multi-mode, and it will bounce off the edges. It's normally also a low-level LED using plastic in the actual cable itself. Single mode, it's actually glass, and inside the single mode there's actually a single light essentially, and that's not bounced off the side. With single mode you can get up to about 10,000 meters, and like I said, it uses the lasers and the glass, whereas the multi-mode can go about 2,000 meters and it uses LED and it's plastic. And it's more secure. More secure meaning it's harder to tap. With your copper cabling, it's relatively easy to actually interpret those voltages and in turn replicate some of that information that's being sent to another host. Okay, so now we know the differences between the fibre and copper cabling. Let's jump into copper cables. There's 3 types I want to discuss. The first being the coaxial cable, or coax, and that's a thick cable shown at the top. Now this cable itself comes in a few forms. The 2 that you're probably going to hear is the RG6, I think it is, which is used in televisions and high-speed internet basically. And we also have the RG59, which is primarily used for patch panels. Now we can see from the actual picture itself there's a thick, very thick plastic jacket that goes around the outside of the actual cable. Then you have this metal shielding, insulation or insulator, and then the actual copper itself. Now this type of cabling was used in the old 10 base 5 and 10 base 2, which is primarily known as thick net, and something else called thin net. And this would be a kind of a bus-like topology where you would have a single cable, and off the back of this cable they would have something called vampire taps, and these vampire taps essentially a teeth, if you like, and they would pierce a hole in the actual wire itself and expose the copper inside, and essentially off the back of that they could actually install a host, and again they would clamp down on that and install a host. And this would be the old way of essentially configuring a Ethernet network, because Ethernet would run through this copper or this coax cable, and the Ethernet would be the layer 2 protocol used. Nowadays we don't use the bus topology like this. We actually use a star, where we have everything connected into a centralized device, and that's normally a switch. And we also don't use the coax cables. We actually use something called twisted pair cables, which we'll come to in a moment. Second cable I want to talk about is the RJ11 cables. RJ11 cables, this guy over here, which is known as your telephone cables. You may notice the end, it's a very small end, and it's actually inside this cable got 2 bits of copper that just run either side, and it would extend the NTE, the network termination, which is inside the premises. Kind of, you have your box from your provider, and you would have out the side of that the RJ11 cable, and that RJ11 cable would sometimes go into your home router, for example, if you had an ADSL technology. Moving on from this, we then have what we use nowadays essentially in most of the copper insulation, and the one that you're familiar with now is the twisted pair. And the twisted pair comes in 2 forms, shielded and unshielded. Now the shielded pair itself is shown on the bottom there. This is the unshielded and this is the shielded. You can see there's a little bit of shielding there, some aluminium essentially, and that would keep any, or attempt to keep any electrical signals from interfering with it. Now inside, as you can probably see better on this picture, the actual cabling itself is twisted. So you'd have multiple pairs. In fact, there's 8 cables, 4 pairs, and the pairs themselves are actually twisted around each other, like so. And then actually in the cable, all those pairs are then twisted together as well. So you have this twisted mesh inside the cable, if you like. And the reason they do that is because, let's say we have our cable and there is some kind of electrical interference. What happens is the twist inside always ensures that there's some copper pulling away from this electrical interference, and in turn it does less damage to the data inside. And this twisting happens on both the unshielded and the shielded. The only difference with the shielded is this extra protection here. 9 out of 10 times is actually the unshielded that you use in the premises and most likely in your offices because of the cost. It tends to cost a lot more for the shielded version of this type of cable. I've also put some comments here regarding RJ45 and Ethernet. Now the comments I want to make around that is RJ45, just like RJ11, is actually the head that goes on the end of it. The RJ45 head looks very similar to the RJ11, the main difference being it's a little bit bigger. The Ethernet element, the reason I've picked that up is because it's important at this level that we understand the differences, just briefly anyway, the differences between Ethernet and copper. Now this type of cable here is very well known as an Ethernet cable, and the reason it's called an Ethernet cable is because 99% of the time is carrying a layer 2 technology called Ethernet, and that's where it gets its name as an Ethernet cable. But what's important distinction here is it's a twisted pair cable that happens to be running the Ethernet at layer 2, and that's where it gets its name as an Ethernet cable. Okay, so when we get later on and we look at this OSI model, the Open System Interconnect model, and we start to understand the differences between physical, data link, network, and so forth, we can then start putting together where these technologies actually separate, because there are overlaps. Like for example here, this is a copper cabling, but we call it Ethernet. Moving on, let's have a discussion around the different types of fibre cables that we have at our disposal. Now we know the differences between copper and fibre and why you might use one over the other, but I just want to touch base on the different types of fibre cables we have. First of all, we have something called a straight tip. The straight tip cable obviously gets its name because of this. It's actually straight on the end, and it has a bayonet sort of screw top here, which essentially you would connect it in and then turn it to lock it. Further to this, we have what's called a field assembly connector, or sometimes referred to as a ferrule connector, and this type of end is a screw-on. So you would actually plug it into the connector and screw it around. It's probably the most secure way of actually ensuring that the fiber's in the port, and depending on like the environment, maybe like an industrial environment, there tend to be the go-to connectors for those. We then have something called a square connector or a subscriber connector, and that's this guy, just down the bottom there, just here. And then we also have, last but not least, the guy just above him, which is the little connector or lucent connector. Now, as you can see, for example, with these guys, there's actually two parts of the cable. One's send, one's receive. And you can actually unclip these and make them essentially, or flip them around. So you'd have send and receive to make some sort of essentially a straight through connector, and then you could flip them around, so you'd have send at one and receive at the other to make what's called a crossover cable. And the different types of cable will be used in different environments depending on why you need each cable. Now we've seen the different types of fibres. How they actually connect into the device varies. The most common type of connectors really are the LCs, the little connectors, and they use something called an SFP. That's a small form factor pluggable, and that's this guy up here. And essentially this small form factor pluggable will plug or essentially go into the device, and then this actual connection here would then slide into the SFP. Now it's important that when you get an SFP that it's the correct SFP, because obviously, as you can tell just looking at this slide, here's just 4 of the fibre connectors, and there's many more. You need to make sure that it's not only the correct physical appearance, meaning is it an SC or an LC, but you also need to make sure whether it's multimodal or single mode, the thing we discussed previously. What I've gone ahead and done is took a photo of a Cisco switch that I have in my house, and this is a Meraki networking switch, or a cloud-based switch they like to call it. And essentially you can see here that there are 2 SFP ports. This particular guy here would just slot into this particular Cisco, and then I'm able to attach this cable into this SFP slot. Now with the Meraki itself, it requires specific SFPs. I can't just go buy one off the shelf and plug it in, so that's another thing you need to put into consideration. And to the left of that, we have all of these connectors. These connectors are just standard home twisted pair, copper twisted pair cabling, and of course they're running the layer 2 protocol Ethernet. In our next section, I just want to whiteboard 2 use case scenarios around how we can use the right cable for the right job. The first one is going to be around a DSL technology example, and the second one will be around a campus network design. So first, if we can imagine that we have our central office or exchange out into maybe the town centre, and from there you have maybe a overhead cable with a few drop points in between that eventually make its way back to your house. When that cable comes into the house itself, it connects into what's called an NTE, and that NTE itself, just like this, will have a RJ11 cable come out of it. Now normally the supplier gives you a 1 or 3 meter cable, and that 1 or 3 meter cable sometimes goes into what's referred to as a splitter or a filter, which then you have maybe your telephone off the back of it, and yeah, that's a terrible telephone. Or it sometimes go directly in to your hardware. So let's say we have a router here. Now these sockets here get sometimes installed in the wrong room, or they get installed somewhere really odd, maybe like the attic or the loft, for example. Now a lot of people, what they tend to do is install another one of these in the house, or what they do is this cable, they go off to the shop and they buy a 10 meter or 20 meter cable. And then what happens is from that actual main socket, they have a very long RJ11 cable. And at the end of that, they then install their router. The problem with this is this particular RJ11 cable, as we know, has just 2 bits of copper in it. And this copper's not twisted or not doing anything special to help with any cable resistance or help with external interference. So essentially what happens is this poor cable here, being designed for telephone and not really extending your router, starts to degrade the overall service. And from the actual exchange perspective, when it runs its dynamic testing to identify the length and quality of the cable, it starts to notice that actually when it does a synchronization check with the actual router, the router seems further than what it should be, or maybe the router itself seems to be on a poor line, and as such you'll see the speeds degrade. Now that's a good example of using the wrong cable for the wrong job. What we should have done is actually left the router where it was, using this 1 or 3 meter cable, and then from the router have the correct cable, in this case RJ45, or as we discussed, twisted copper pairs. If I actually wrote RJ45 correctly. And then on the back of this RJ45 cable, we'd have our devices connected. May that be a PC, or it could be connected to a switch in another room, which then our devices connect to. This correct use of cabling will actually ensure that the exchange itself will see the correct length of cabling and the correct quality of cabling, therefore giving us the speed that we require. And this cable itself, as we discussed, can go up to 100 meters, so you have that extension around the premises. And that's a home premises example of using the correct cable for the right job. Now let's grow on this and have a look at a campus design. Now what I mean by campus design is campuses are normally designed on 2 or 3 layer structures. So let me draw one for you. Let's say we have 2 switches, and the back of these switches we've got a bunch of actual PCs connecting into them. Normally these switches will have a uplink, and that uplink is normally a resilient uplink, like so, into another layer of switches, this known as the distribution and this known as the access. Now this access and distribution, depending on the size of the campus, could actually all live in one very big cabinet. However, depending on whether it's a collapsed core or whether it has an actual 3-tier hierarchical design with a core elsewhere, your core is normally located further away from this kind of physical rack. Now if that was the case and the core was located more than, let's say, 100 meters away, then we need to have a think about what sort of cable we should be using there. Because we know that copper cabling, at least without any repeaters or devices in the middle, can only travel so far. So we may need to think about using a fiber connection there, maybe utilizing the multi-mode with the LEDs and ensuring that we have the SFP modules at both ends and actually utilizing fiber instead of copper. And that's another use case of using the right cable for the right job, but in a campus design instead of a home environment. Okay, so that's all we've got time for this lesson. Let's wrap up what we've actually learned. We've first touched base on the differences between copper and fiber. We know that copper is prone to interference and fiber is not. Fiber is more secure than copper. We then went into the different types of copper, understanding what's twisted pair and RJ11 and coax cables. And we touched base on the old way of Ethernet and how it used to work in 10-base-5 and 10-base-2. We then went straight into fiber connections and fiber cables, understanding what's straight tip and square connector and ferrule connectors, and ultimately what's required to connect those devices up using the small form factor pluggables, the SFPs. And then we had a quick whiteboard discussion around using the right cable for the right job, looking at a home DSL connectivity and actually a campus hierarchical design. I hope this video has been informative and I'd like to thank you for viewing, and if it has been, please do like and subscribe.